If you slice your golf ball deep into the woods, your brain, immediately tells you that you swung the club in the wrong direction. You think, you chopped across it.
Right, that's the natural assumption.
Yeah, but physics tells us something completely counterintuitive. 80% of your mistake had absolutely nothing to do with the direction your club was actually traveling.
It's crazy to think about.
It really is. I mean, think about that for a second. The vast majority of our frustration on the golf course comes from a total misunderstanding of the basic physics happening right at the moment of impact.
Yeah, it is the ultimate biomechanical illusion. A golf swing looks like this fluid, sweeping arc, but what we are really analyzing is a highly volatile collision.
A very fast collision.
Exactly. That collision happens in less than a millisecond. And as you just pointed out, the human brain is remarkably bad at diagnosing what goes wrong during that tiny fraction of time. We just end up trying to fix the wrong variables.
Which is the entire mission for today's deep dive. We are unpacking the exact biomechanics of the golf swing for you. We want to know precisely what separates a weak, frustrating amateur slice from a tour-level explosive strike.
I've got a lot of data to back this up.
Oh, absolutely. To do that, we've pulled together a massive stack of sources. We have advanced sports science journals breaking down swing kinematics, including some really eye-opening cross-sectional data, specifically on female professional golfers.
Which is super important context.
Definitely. We've also got medical literature detailing the brutal physiological toll these swings take on human tendons. And finally, we are venturing into the cutting-edge world of AI and wearable tech to see if we can essentially put a digital PGA coach right in your pocket.
The landscape of sports science has completely transformed here. We used to rely entirely on a coach's naked eye to, guess why a ball slice.
Right, just standing on the range squinting.
Yeah. But today, we are capturing joint angular velocities at 1,000 frames per second. We can measure the exact degree of biomechanical failure in real time.
Okay, let's unpack this. Because before we can strap on the latest wearable sensor to fix your swing, we have to understand the actual physics of why a golf ball goes where it goes. Let's go back to that counterintuitive fact I mentioned at the top.
80-20 rule.
Exactly. Break that down for us.
So, in ball flight kinematics, the initial launch direction of the golf ball, what we call the initial azimuth, is highly skewed toward one specific variable. When the club head strikes the ball, approximately 80% of that starting direction is dictated purely by the face angle of the club.
80%? That's massive.
It is. The actual path the club is traveling through the air only accounts for the remaining 20%.
I always picture it like driving a car, the face angle is your steering wheel, and the club path is the direction the physical road is heading.
That's a great way to visualize it.
Right, so if your road is curving to the left, but you crank your steering wheel hard to the right, your car is violently careening off into the right ditch.
And a slice is born exactly from that mismatch. For a right-handed golfer, a slice is a ball flight that starts out heading left or straight and then curves dramatically away from the lead side, ending up deep in the right rough.
So what is mechanically happening in the body to cause that mismatch? I mean, if the steering wheel is pointed right, why is the road going left?
The root cause is a pathomechanical chain reaction. It usually begins during the transition from the backswing to the downswing. The amateur golfer allows their lead wrist, so the left wrist, for a right-handed player to extend.
Okay.
In golf terms, they cuck the wrist. The moment you cuck that lead wrist, the club face artificially rotates wide open relative to the swing plane.
So the steering wheel is now cranked to the right. But your brain subconsciously senses this, doesn't it? Even if you don't know the physics, your body realizes the face is wide open.
Oh, absolutely. The central nervous system goes into an instant panic mode.
It knows you're in trouble.
Right. The brain calculates that if you just swing your arms down naturally from that position, the ball will shoot directly sideways. So to save the shot, the body instinctively tries to pull the entire path of the swing hard to the left to compensate.
Oh.
The golfer executes this premature, aggressive rotation of their upper thoracic spine. They spin their shoulders out way too early.
Which instructors call the upper body dive, or the classic over-the-top move.
Exactly. That panic rotation throws the hands outward, pushing the club shaft onto a very steep out-to-in delivery path.
So now you've got a club traveling sharply across the ball from the outside in.
Right, combined with the club face that is still sitting wide open. That intense friction creates massive lateral spin, resulting in a weak, high slice that completely lacks compression.
It's just a desperate spatial compensation. But if the face ankle is the steering wheel and amateurs are constantly fighting it from opening up, how do the pros hold it so perfectly steady through such an explosive swing? I mean, they aren't just gripping the club tighter, right?
Far from it. Attempting to manually steer the face square with muscle tension actually slows the club down.
Makes sense.
Elite ball strikers rely on a highly specific triplanar sequence of wrist and forearm movements during the downswing transition. They use supination paired with flexion.
Hold on, triplanar, you're losing me there. I just want to hit the ball straight. What does that actually look like in human terms? Let's ground this a bit.
Fair enough. Think of the forearm and wrist not as a simple hinge, but as a complex multidirectional joint. Supination is the outward rotation of your lead arm.
Okay.
If you hold your left arm out in front of you, it's the counterclockwise rotation of the entire forearm so your palm faces upward.
Here's where it gets really interesting. I was reading through the sources, and the best visual for supination is imagining you are standing at the edge of a lake, gently skipping a stone.
Yes, perfect analogy.
You aren't just flipping your wrist up and down,
Yeah.
Your entire forearm rotates to turn your palm toward the sky through the release.
And that rotational movement is mandatory because every single club face naturally rotates open during the backswing. Without supinating the lead forearm on the downswing, squaring the face is physically impossible.
But supination alone isn't enough.
No, supination alone just leads to a high, weak shot. To truly trap and compress the golf ball, that rotation must be paired with lead wrist flexion.
And flexion is the exact opposite of that cupped wrist that causes the slice. It is the palmar bending of the wrist like, physically bowing it outward toward the target.
Correct. Combining those two, supinating the forearm while aggressively bowing the wrist, is the true secret to ball striking. It allows a player to drastically de-loft the golf club as they approach impact.
There was a brilliant demonstration of this in the materials by PGA coach Zach Allen. He uses a very basic training aid called a golf hanger.
Oh yeah, that's a classic drill.
Yeah, you can literally just take a plastic coat hanger and press it against the grip of your club. As you swing, the entire goal is to keep the plastic hanger pressed firmly against the inside of your lead forearm.
Which forces the correct mechanics.
Exactly. To accomplish that, you are physically forced to supinate and bow that wrist. Allen showed that by maintaining that pressure, he could take a standard 9-iron, which normally has 43 degrees of loft, and deliver it to the ball with only 31 degrees of dynamic loft.
He basically turned a 9-iron into a 6-iron.
Right.
By delivering less loft but maintaining the shorter, more controllable shaft of the 9-iron, the ball compresses violently against the turf. It launches lower, but with a much higher energy transfer.
And this dictates the entire release of the club. Elite players like Dustin Johnson or Scotty Scheffler bow that lead wrist and supinate early in the downswing.
Yes, their club face is essentially square when the club is still waist high.
What's fascinating here is that because they aren't panicked about an open face, they don't have to stall their body rotation.
Exactly. They don't have to rely on perfectly timed hand flipping at the bottom of the swing to save the shot. They maintain that forward shaft, lean and aggressively rotate their pelvis and chest.
Pulling the club handle continuously down the hand arc path.
Right. They let their body rotation power the strike rather than their hands.
Wait, if I'm rotating my entire forearm and violently bowing my wrist while pulling against the centrifugal force of a 100-mile-per-hour swing, my joints have to be taking an absolute beating, right? We have to look at the physical implications here.
Oh, they definitely are. The medical literature makes it very clear that the golf swing is a massive trauma event for the soft tissue of the arms.
I can't imagine.
When that club head strikes the turf and the ball, a violent kinetic shockwave travels up the steel shaft directly into your hands and dissipates right into your forearm tendons.
Ouch.
Yeah, and your specific swing mechanics dictate exactly which tendons are going to tear.
Let's start with lateral epicondylitis, which is commonly known as tennis elbow. This is pain on the outside of the elbow, and ironically, it is the injury that absolutely plagues amateur golfers who slice the ball.
The mechanism of injury goes right back to that chicken wing release we see in amateurs.
The classic chicken wing flapping.
Exactly. Because the amateur leaves the club face open and tries to scoop the ball into the air, the lead wrist breaks down into extension. As they hit the ground, the lead elbow flares sharply outward.
Physiologically, it is a catastrophic position to absorb force, isn't it?
It's terrible. To try and stabilize that collapsing, scooping wrist at impact, the extensor muscles on the back of the forearm, specifically the extensor carpi radialis brevis, are forced to rapidly contract without changing length.
So it's an isometric contraction.
Right.
So instead of the muscle stretching to absorb the blow, it clenches up like a rigid brick wall.
A brick wall that a high-speed shock wave is about to slam into.
Wow.
That sudden, violent impact against a rigidly contracted muscle causes severe microtears where the tendon attaches to the lateral epicondyle of the humerus. That repeated trauma is tennis elbow.
Wait, so you're telling me that if I fix my slice, learn to beautifully bow my wrist, and finally start striking the ball with massive compression like a tour pro, my reward is just shifting the trauma to the other side of my arm and getting golfer's elbow instead?
Unfortunately, yes. Medial epicondylitis is incredibly common among highly skilled players. The pathology just shifts from the outside of the arm to the anterior flexor compartment, the muscles on the inside of the elbow, like the pronator teres.
Because those are the muscles doing the heavy lifting for all that flexion and supination.
Exactly. When an elite player flexes the wrist and grips the club tightly to generate massive lag and club head speed, they place explosive eccentric and concentric loading on the common flexor tendon.
It's just so much force.
The sheer repetitive stress of sustaining those extreme joint angles against the turf impact leads to chronic inflammation on the medial side of the elbow. It is literally the physical tax they pay for elite biomechanics.
That is wild. The better you get, you just invent new ways to tear your arm apart.
Basically.
But this highlights a major problem. Feeling these precise wrist angles, knowing if you are supinating correctly to fix your slice or just setting yourself up for an overuse injury is nearly impossible to do by yourself.
Because the arms are moving way too fast for the conscious brain to process.
Right, which is why the golf instruction world is in the middle of a massive technological arms race.
The shift from subjective visual coaching to objective kinematic data is revolutionary. We are looking at real-time telemetry instead of just drawing lines on an iPad screen.
Our sources highlight two main schools of thought battling for supremacy here: wearable IMU sensors versus vision-based AI cameras.
Both have huge implications.
Let's look at the wearables first. One of the dominant tools is HackMotion. It's a 50-gram sensor you strap to your lead wrist. It uses gyroscopes and accelerometers to measure your exact degrees of flexion and extension throughout the entire swing.
And then it compares your angles to PGA Tour benchmarks.
Right. It isolates the single most important variable for club face control. But another wearable, DeWiz, takes a completely different neurological approach. It also sits on the wrist, but it focuses on tempo and transition sequencing, and it utilizes something called learning stimuli,
Which is a fascinating concept.
which is a very polite corporate term for a device that literally shocks you. If your backswing gets too long or your transition gets too steep, the device delivers a mild haptic electric pulse to your wrist mid-swing. We are essentially gamifying pain to fix a golf swing.
It sounds extreme, I know. But the science behind it is incredible. It relies on instant neurofeedback.
How does that bypass normal learning?
Well, verbal instruction from a coach requires the conscious brain to process the words and then attempt to translate them into motor commands.
Which takes time.
Right. By delivering a physical haptic shock, the exact millisecond the swing path deviates, it bypasses the conscious brain entirely. It forces the central nervous system to rewrite its motor pathways on a subconscious level just to avoid the stimulus.
So what does this all mean for the other side of the tech divide? We have vision-based AI platforms that require no wearables at all. You just set up your phone.
Apps like Watch It Golf are utilizing the dual camera setups and LiDAR scanners built into modern smartphones.
And LiDAR is crucial there, right?
Right. Very. Because it measures actual depth by bouncing lasers off the golfer, calibrating the exact size of the ball and the human body down to a centimeter.
And then you have platforms like Joewi, which uses markerless tracking to map 17 different body key points at 30 frames per second from just a standard video.
Yeah, that software is getting so advanced.
It analyzes the sequencing of your pelvis, which it calls the engine, and the release of your arms, which it calls the WHIP. But if you are a player trying to improve, what is the actual trade-off between wearing a sensor and just using a camera?
If we connect this to the bigger picture, it really comes down to physical encumbrance versus optical reliability.
Break that down.
Wearable IMUs provide incredibly precise temporal and rotational data because they are physically attached to the joint. However, they suffer from sensor drift.
Like a compass that slowly loses true north the longer you walk.
Exactly. If the strap slips even a fraction of a millimeter on your sweaty arm, the internal gyroscopes calculate the starting position incorrectly, and your data is ruined.
I see.
Vision-based AI solves the encumbrance issue. You aren't wearing a bulky watch that might alter your natural swing feel. But 2D cameras introduce parallax errors.
Parallax errors.
Yeah, if the smartphone isn't perfectly aligned with your center of mass and the target line, the software lacks the 3D context to calculate joint angles accurately. An arm pointing straight at a misaligned camera looks artificially shorter to the AI.
So the data is only as good as the setup. But having mountains of precise data is totally useless if you don't have the context to apply it. The golf swing is not a monolith.
No, not at all.
It changes drastically based on what club you are holding, and more importantly, based on your own physical body.
We cannot apply a generic textbook mechanical model to every human being. The biomechanics must be scaled to the individual.
Right. Our sources included a fascinating cross-sectional study published in Frontiers that looks specifically at female professional golfers.
This was a landmark study.
Because historically, golf instruction was dominated by male-centric models. But this study proved that female pros exhibit significantly different angular velocities at the wrist and elbow joints compared to their male counterparts.
The data points to highly evolved, sex-specific swing strategies. Female professionals are organizing their kinetic chain differently to optimize power.
Due to anthropometrics, right?
Exactly. Because of differences in overall mass, leverage, and center of gravity, their anthropometrics, they must sequence their joint rotations differently to maximize club head speed.
Let's ground that term, anthropometrics. We are talking about their actual physical wingspan, height, and muscle distribution dictating the swing, not just a theory in a book.
Spot on.
And the study showed those mechanics completely shift depending on the club in their hand. When hitting a driver, the data showed a massive increase in torso rotational amplitude.
Because the goal is accumulating kinetic energy for an aggressive sweeping blow.
Right, but with a 7-iron, the mechanics tightened up. The focus shifted to precision, postural balance, and steepening the angle of attack.
Yet, across all those mechanical changes, from the driver to the wedge, there was one incredible constant among all elite players.
The concept of the quiet eye.
Yes, the Vickers theory. This is where it all comes together. The head and neck serve as the structural foundation for your visual and vestibular systems. The study highlighted that regardless of how violently the body was rotating, the elite players minimized head movement to an astonishing degree.
It makes me think of a sniper holding their breath right before pulling the trigger. That intense vestibular stability prevents gaze deviation.
It's essential.
It is the absolute foundation for spatial perception, allowing the brain to deliver that club face squarely to the ball.
This raises an important question, though. It leaves coaches with a massive responsibility. If mechanics change based on gender, anthropometrics, and the club being used, coaches cannot simply force every student into a cookie-cutter mold based on AI data.
They have to act as translators.
Exactly.
It's the art of coaching meeting the cold science of biomechanics. Let's take a breath and recap this incredible journey. We started by realizing that the 80-20 physics of the slice means the face angle our steering wheel dictates the shot.
We broke down how pros trap the ball by supinating the forearm and bowing the wrist to deal off the club.
Right, and we explored the violent shock waves that travel up the shaft, trading the amateur's tennis elbow for the elite's golfer's elbow.
And we mapped the technological arms race between neuroplastic wearables and LiDAR vision tracking.
Proving that all this data must be adapted to a player's unique physical realities. It is a profound look at how much complexity is hidden inside the simple act of hitting a ball with a stick.
It really is.
Before we wrap up, I want to leave you with one final provocative thought from our stack of research.
Oh, this is the IE paper.
Yes. Right now, we are strapping sensors to our wrists and pointing phone cameras at our bodies to analyze the swing from the outside in. But buried in our sources is a recent paper from the IE Sensors Journal. Researchers are currently using self-supervised learning and deep neural networks to build sensors directly into the hollow steel shaft of the golf club itself.
The equipment essentially becomes a living diagnostic tool.
Exactly. They are using complex ResNet architectures where tiny piezoceramic sensors inside the shaft interpret the acoustic and vibrational frequencies of the strike. These smart clubs can instantly detect not just your swing path, but the exact millimeter impact location on the club face in real time with over 93% accuracy.
That removes the need for external cameras entirely. The club literally feels the shot for you.
So ponder this for a second. When the golf club itself becomes an artificially intelligent, self-contained system that knows exactly how you hit the ball through micro vibrations, will human coaching eventually become obsolete?
That's the million-dollar question.
Or, in a world where amateurs are absolutely drowning in instantaneous biometric feedback, Will we actually need expert PGA professionals more than ever just to filter out the noise and translate that data into a confident, free-flowing swing?
I'd argue the latter. The technology will always be able to tell you the what and the why, but the human element is required to teach you the how.
I think you're absolutely right. Hey, if you enjoyed today's deep dive, please subscribe to our channel and share it with fellow golfers, coaches, and PGA professionals. Whether your interest is ground reaction forces, swing mechanics, club fitting, or sports science, we want to hear from you. Feel free to connect with us on LinkedIn or email us your ideas, and you might just inspire a future deep dive for the eCoach 360 community.
It's a great community to be a part of.
Absolutely. So, next time you are on the driving range and you see that ball start to violently drift, right? Remember, you don't need to panic and spin your shoulders. Just check that tiny loose screw, fix your steering wheel, and trust the physics. Thanks for diving deep with us today. We'll see you next time.